So, one-dimension momentum, and what does KE stand for again? Right now? Okay, so recall. What's the formula for momentum? Actually, what is the letter? Yeah, it's P. I don't remember why. It's probably a Latin thing. Like, why is lead PB?
That's like some old Latin word.
Yeah, it's a word, right, that they took it from. So anyway, it's P, and it's a product of mass and velocity. I just pops into my head, sports like rugby and football. You want people with lots of momentum. They're hard to stop, right? Sure, sometimes they're hard to get going, but once they're going, boy, they're hard to stop. This is a vector quantity, meaning what? It has, yeah, magnitude and direction. So some books would actually put it with a little arrow on top to indicate that's a vector, but I just tell you it's a vector and you need to know it. Okay, what is change in momentum? It's got a word. Yeah, it's delta P, but yeah, it's got a word. It's called impulse. Again, I don't know where that comes from, but change in P, the mass doesn't change. So where we put the change in is the velocity. And if some guy who's playing football happens to be running at some speed and I stop him, I put an impulse into him, and his speed, it's always final minus initial. Okay, it'll be a negative. Because if I took his momentum as positive, then to change that and make him stop, it's in the other direction, right? Now, because F is ma, and by definition, acceleration is a change in velocity over a change in time, and I can put, well, that is momentum, isn't it? That's impulse. That's a change in momentum right there. If I times both sides by delta t, then I can get this formula and go F times delta t is m times delta v, and then this I can also call impulse, because that is change in momentum. So that's another formula I can use. So example, a 1100 kilogram car hits a wall at 20 meters per second, and it could, I guess, go through the wall, but I'm telling you it doesn't. Comes to rest. If the car contacts the wall for 1 second, that would be a change in the time. 1 second. What force is exerted? Now that same force on the car, it's the same force on you, because you're kind of attached to the car, okay? Not taking into account seat belt or an airbag, okay? Because there's lots of things we assume, right? No friction. Well, what do I got? F is m delta v divided by delta t. I got a mass. What's my change in the velocity? Change in is final minus initial, which is my final, yeah, is 0. My initial is 20, so So my change in is negative 20 meters a second, and my change in the time is 1. So that is 22,000, and I got a negative sign, implying that the force is in the opposite direction that the thing was going. And you kind of common sense, right? Because I took this way as positive, so if I stopped it, it had to be a negative. Force is in it. So, piece of cake, right? Another one. And this was tricky in grade 11. Where you been? What were you answer a phone call? Something? Huh? A 100 grammage 10E ball hits a wall, and what's a good word for going the other direction after hitting a wall? Hey, bounces, rebounds. Oh, I forgot this. Same speed. So hits a wall at 20 meters a second and rebounds at 15. What's the impulse imparted on the ball? I won't write the next part down, we'll just maybe discuss it. Impulse, what's that? Well, I don't know. It's that, the full formula, like the left side's impulse, but it's equal to the right side, so that's also impulse. Impulse is change in momentum, however way you want to think about it. Okay, well, what do? First of all, I don't want grams, do I? 0.1 kilograms. What's my change in the speed? Again, this was tricky in grade 11, right? So, pictures are handy. There's my wall. It comes in that way at 20 and hits it and bounces back at 15. But there's a sign problem here, right? If I'm taking that way as positive, the other direction, that's got to be a negative. Because when I take the change in, it's not 5. What's the change in the speed here? Final minus initial. Final, if I'm taking that way as positive, that way is negative, minus 20, my change in the speed is negative 35 meters a second, okay? So then my impulse is 0.1 times the change in the speed, which is 3.5. Negative just implies the direction. And that's kilogram meter a second. Impulse. No, it's change in momentum. So there isn't a special symbol for impulse. Okay, it's not I or anything. Yeah, it's that's the units, right? It's not a force. It's a force times a time. It's Newton seconds, if you want to use those units, or kilograms meters per second. Either of those are fine. They're equivalent. Okay? No, F times T. Newton seconds. Okay? So, if it didn't rebound, if it just hit the wall and dropped or stuck, if it was plasticine and not a tennis ball, that puts it in things we know, common sense. Is it more or less momentum? Sorry. Impulse. Is it more or less impulse? Less, yeah. Okay, it's less. because the final would be 0, right? So 0 minus 20, it would just be 20 if it hit the wall and stuck, right? And just dropped straight down, which is then just, well, using the same sign, 2. Okay? More impulse if it bounces off. Okay, so that's all review, really, right? That's recall. Nothing new there. This still isn't anything new. Did you do any two-dimensional momentum last year? No? You did conservation of momentum? Okay. Recall. Momentum in a closed, isolated system is always conserved. And I told you guys way back before radar guns or things, this is actually how they calculated how fast bullets went. They shot them in blocks of wood. You could actually measure how fast the wood went after it was in there. You can't see the bullet going by. There's nothing, I don't even think now, most radar guns don't pick it up. It's something really high-end and specialized, which is quite modern. Even I'm going to guess, I don't know, off the top of my head, in the last 10, 15 years, we might have something now to calculate it. But your good old radar gun that you guys get speeding tickets with, that doesn't pick up a bullet. So this is how they actually calculated it, 100, 200, 300 years ago, how fast this thing actually went. Momentum is always conserved. And a closed, isolated system, this is just some caveat, right? Like when we're doing math and we say, well, the denominator can't be 0, that type of stuff. This is the only stuff you're going to get. So you can kind of just know momentum's conserved. You do that every time, and you're going to get your problems correct. Okay, but now we got to add something. We're going to add kinetic energy. Billiard balls, i.e. pool. They don't call it pool in UK, it's billiards. Pool means swimming. So that's just kind of like a North American kind of term, right, Meryl? Huh? Yeah, she knows it. I'm going to write something else, but as far as kinetic energy is conserved, or is it not conserved, we have to look at each collision and interpret what's going on. And we're going to calculate whether kinetic energy, which by the way is, as a formula, 1/2 mv squared. That's the same 2 units of momentum, isn't it? Only we're taking half of it and we're squaring v. That's kinetic energy, if you recall. So you know what billiard balls do? They're like hard, right? Are they porcelain, ceramic, or are they actually made of stone? All of the above. I think the really, really good sets, they actually do make them of like a marble or a stone, something natural, but it's really hard to make them perfectly spherical. So like anything in life, the more you pay, the better quality you get. That's quite a bit different than a car crash where you want this thing to crumple. You want it to absorb some of the energy, because the more that the car absorbs, the less that goes to you. Okay, modern cars are designed to do this. They're designed to crumple and crash. The exterior of it, right? The cabin, we don't, because then, of course, it's going to come and hit you. Old cars, some people think they're actually safer because they're built like tanks. Well, the car looks a lot better after an accident, but as far as the G-forces go into you, they're a lot greater, right? They're a lot more unsafe. So it's not what the car looks like. So one of these kinetic energy is conserved and one of them isn't. Do you see which one is which? Do you have any guesses? Billiard balls, which one? Kinetic energy conserved or not conserved? Is it converted to other forms? Yeah, it is, right? Pretty much you hit that one cue ball and it hits that other cue ball, and pretty much like this one stops and this one continues on, and it looks like the same speed that this guy had. So you could kind of argue, well, 1/2 mv squared before kind of equals 1/2 mv squared after. I know some of that energy is conserved to something else because I hear the collision, so it's not exactly 100%, but 99.9% of it is conserved in billiards till it hits the bumpers, right? And you still get a good bounce off of them if they're nice and fresh, that nice natural gum rubber that they can use in the good ones. But some of it, if they hit it there 100 times and you measured the temperature of that bumper compared to the other bumper, it would be hotter. Some of that is converted into heat in other forms. So this energy is conserved, kinetic energy. Here, kinetic energy is not. It's converted into other forms. We want it to crumple and heat up because the less energy goes to us. So there's two words here. Okay, and I could have just wrote this out. One is an elastic collision, and one is an inelastic collision. Okay, there's the two terms. For billiard balls, we know kinetic energy is conserved. Which term do you think would apply there? Elastic? You guessed that correctly. I'm trying to figure out why. Because to me, that word is, when I think of elastic, don't you think of elastic band? Something rubbery that gives?
I was thinking of, if you watch other lists, like you shoot somebody golfing, ball on two creases, and then it
Okay, but that's not a billiard ball. That's a chunk of
it's
stone.
The same thing, just less. It's the
Okay.
same
Oh,
concept.
well, I should have just wrote it out. All right. And this is one of these things I find it really hard to remember because it's the opposite of how it should be. Billiard balls do not give, like they're rocks. How much can you compress a billiard ball? Not a heck of a lot. That is an elastic collision. And how do I remember that? Because I know that's so far from like rubber, it doesn't make any sense. I would think that, I don't come up with these terms. I'm just like you. I'm forced to memorize them, even if they don't make sense. So, that is an elastic collision. This is what does make sense. In an elastic collision, not just billiard balls, but anything I tell you that's elastic, kinetic energy is conserved. Okay, so once you know one, well, the other one's easy. That's inelastic. Kinetic energy is not conserved. So, two cars that crash, their kinetic energies before 1/2 mv squared plus 1/2 mv squared will be some number. Afterwards, a lot of that kinetic energy is converted into heat and sound. It's pretty loud, right? Sound's really small compared to heat, but it does still get converted into there. After, the kinetic energies will be a lot smaller. All right? Momentum's always conserved. Actually, total energy is also always conserved. But kinetic energy is just one part of the energy, okay? So conservation of energy, it's always conserved. But not kinetic. Other forms. Okay. Example. So, 900 kilogram car traveling at 10 meters a second. collides and sticks to... Can billiard balls stick? Yeah, it looks like it. It can look like it. If one has spin, it looks like they can be right together. But being elastic, I'm saying they can't. Okay? All right? So when sticks to, what does that imply? Yeah, inelastic collision. Now we got to think in physics 12 terms, not just physics 11 terms. So sticks to a 1,000 kilogram car at rest. We know the speed there. What is the resultant velocity? Of which car? Does it say? Both. They're stuck together, right? That's what that says. So, again, this was tricky for some of you guys. Momentum is conserved. Always, always, always. Means whatever momentum I had before, that's the same amount of momentum I had after. Before, and if you want to draw a picture, okay, this is before. I have this car and I have that car. This guy is 900 and it's moving at 10 meters a second. This guy's 1,000, but it's at rest. After, they're stuck together. So I have a combined mass. What is the resultant velocity? Okay, there's a picture of exactly what I said in words. If it's helpful, use it. I recommend it. Some of you guys won't. So before I have MV of the first car and MV of the second car equals MV of the first car after an MV of the second car after. Okay? But that's 900 times 10. What's the speed of the second guy? Yeah. So I didn't need to put that in there. And then after I have, well, let's put all on my numbers. These are combined. So I'm going to factor out M. All I want to know is, and this means prime, which a lot of the books, if you see it some other places, you'll see it means after. And they'll even go A, B, whoop, A, B, B, that's A, okay, but it gets really confusing, okay? So, that's all I have before, just the momentum of the first car, because the second car had no momentum. After, I want to know what the velocity of these two guys combined is. That divided by that, I got 4.7 meters per second. But is that a speed or a velocity? That is a velocity. I should have direction here. I took right as a positive. This came out as positive. Therefore, these two masses are all going the same direction, right? So, there. Now I have direction. Okay, it's not always going to be in the same direction. If this guy's coming that way, I have no idea what the second guy will be doing. He might go that way after the collision, he might go this way, okay? So you got to pay attention to direction now. In this case, they're both going right, and we would assume that. That's just kind of common sense, right? How on earth could they go left?
So what happened to the energy? What energy?
Well, I never asked that in this question, but I will. Give me a sec. Okay, that's just momentum. What's the resultant velocity? Okay, I got more examples. Let's do an explosion. A stationary spaceman of 120 kilograms needs to go back to his spaceship. I'm not writing that, I'm just saying it. Shoots 100 grams of gas. He's got an air horn, right? Assuming that it works in space, where there's no pressure, okay? I could have said he threw a wrench. Something. What is the resultant speed of the spaceman? That is an explosion. Two things are breaking apart. Okay, sorry it's not as cool as like a grenade. That's an explosion. Momentum before is momentum after. How much momentum is there before? There is none, yeah. How much is there after? Well, I have him and I don't know what speed he's doing, and I also have this gas. Now, technically, this gas is combined with his mass before, right? So it's 120.1. That is really, really insignificant, but I should actually add it. But I won't, because it's not going to make that big of a difference. Okay? So, I got a guy. This is before. And then after, okay, he shoots this in that direction at 100 meters a second. Well, what way is he going to go? Yeah. So whatever direction you want to go, you got to spray this in the exact 180 degrees of that, right? I want to go that way, I got to spray this thing that way. Okay, so I've got this m times v. That's after. It's in the other direction though, isn't it? Hold that thought. Because when I bring this to the other side, what's 1/10 of 100? V is 1/12, which is negative. That's what I was trying to say. Pretty small speed, but again, look at the difference in the inertia. So, why is that negative? Because it's going the other direction. Yeah, I took that way as positive, so that way is negative. Okay? Last one. Now let's look at some energy. A 1,100 kilogram car. Traveling west at 8 meters a second. Hits a 1,000 kilogram car at rest. Sitting at a stoplight, whatever. After impact, the first car travels at 2 meters a second west. Do we assume they're stuck together? No. No. Because it's telling you about the first car, but it doesn't say anything about the second car. It doesn't say they're stuck together. A. Is momentum conserved? B. Is collision elastic? I won't write C, even though I have it here, but I'll just talk about it. A is easy. Is momentum conserved? Always. Yes. If it's not, how on earth can you solve the question? Is the collision elastic? Okay, new stuff. What do I know about elastic collisions? Kinetic energy is conserved. Okay, so is kinetic energy conserved? I answered A. I'm doing B. I'm answering B, right? Okay, A. Always B. If I know that, then I know this. What do I know about kinetic energy? I know a formula is 1/2 mv squared before equal 1/2 mv squared after. If it is, then energy is conserved and it's elastic. And if it isn't, then it's not. So I need 1/2 mv squared for the first car, because it's the whole thing, right? And 1/2 mv squared for the second car before, and 1/2 mv squared after for the first car, and 1/2 mv squared for the second car after. Is that equal? If it is, it's elastic. And if it's not, it's not. Do I have M and V for the car before, the first one? Yeah. Do I have M and V for the second car before? Yeah. Do I have M and V for the first car after? Yeah. Do I have V for the second car after? No, I don't. It doesn't say they're stuck together. I don't know this. All right? V after for second car. So guess how I'm going to solve for that? Conservation of momentum. Even though it's not even asking me for the velocity of the second car, I need it to answer this. Oh boy, what could be funner? Okay, so momentum. Before I've got, and I'm not going to write all the formulas down, I'm just going to whip in here. I'm going to take west as positive. Okay? West is positive. So now I don't have to worry about direction. I'm just going to put that is positive. And what's the momentum of the second car? Before? Nothing. I'm not even going to put it there. So that's momentum before. What's momentum after? The first car travels at 2 meters a second. Is this positive or negative? Positive. West is positive. But what I don't know is, what's the speed of the second car after? So I need to solve that for V, stick it in here, and then solve this guy. Okay, so what's 1100 times 8? Yeah, that's right. Why am I doing that in my calculator? Okay, minus that is 1000 V. Okay, so that minus that is 6600 over 1000 is, looks like about 6.6, right? What direction? Came out as positive, so that's west. Okay, so you draw yourself a picture, but it's going the same direction after it hits. They're both going the same direction, which should make sense. No, this is momentum. I'm doing momentum. I got to find V. This is momentum. There's no squared V here. Oh, stand by, stand by. Okay, so that's V. Now I got to find out if energy is conserved. KE. I got 1/2. The first car was at 1100, yeah. And V was 8. Does it matter what direction? Does that matter? Is energy a vector? Can I have 1000 joules from a Coke bottle west? No, it's a scalar. There's no direction. And the formula, even if it's a negative or positive, it doesn't matter. You get the same thing, right? And this guy times, what was its speed before? Oh, that's easy. Is that equal to, and I could have put left or right or something. This guy after is doing what? 2 squared, and 1/2 1000. This guy is doing 6.6 squared. Okay. Whoa. Doing some math. 1/2 1100 is 1100 divided by 2 times 64 plus 1/2 of 1000 is 500 times 0 is nothing, right? So energy before is 35,200. What do I got after? Let's do it differently. 0.5 times 1100 times 4 plus 500 times 6.6 squared. 23,980. Is this an elastic collision? No. KE is not conserved. I lost some. Where do you think it went? You bet. But don't just assume because you see a car crash, because I'm going to give you problems where it is conserved, which isn't really realistic, but you don't just say it's a car crash, therefore energy is lost to heat. And sound, that's the two main ones, I guess, right? Okay. 1 to 5 and 7.